closely at a high-speed automotive sensor or a modern 5G module, and you'll see a pristine, organized grid of components. But if you zoom in past the packaging, down into the microscopic canyons of the copper traces, the physical reality is entirely different. Hardware engineers are currently operating in an environment where digital signaling speeds routinely cross into the multi-gigahertz range, all while component footprints are compressed to absolute minimums. To navigate this complexity, we must look at the data. This technical breakdown, presented by Moldart, examines the precise physics of modern board manufacturing. For decades, the industry has relied on a procurement model prioritizing the initial invoice price of a bare printed circuit board above all engineering metrics. At modern frequencies, structural and surface fidelity operate as fundamental EMI certifications and field failures. The math dictates a clear inverse relationship. By increasing the initial unit investment, a firm can mathematically shrink the probability of these expensive failures. This technical precision model provides a framework for identifying where upfront material and process quality can neutralize the volatility of the risk-cost variable. The physical necessity of this strategy becomes obvious when you push alternating current into the 5 to 10 GHz range. This diagram demonstrates the skins, and the current abandons the center, crowding tightly into a microscopically thin layer at the very perimeter of the conductor. Because the signal travels exclusively near the surface, microscopic roughness at that outer edge directly dictates signal survival. If the copper profile is rough, the signal will collide with those peaks and valleys, resulting in a 10 to 20% increase in insertion loss. The choice of surface finish directly impacts this effective conductivity. Standard electroless nickel immersion gold, or ENIC, contains a ferromagnetic nickel layer that strips energy from signals exceeding 1 GHz. A high-fidelity finish like immersion silver removes the nickel entirely. To maintain a viable signal-to-noise ratio in modern 5G and radar architectures, select the localized dielectric constant, or DK. Standard boards are built from a woven matrix of fiberglass bundles and epoxy resin. The glass bundles have a dielectric constant of roughly 6.0, while the surrounding resin gaps sit much lower, at roughly 3.0. This creates the fiber weave effect. If you route a high-speed differential pair so that one trace travels over dense glass and its partner travels over resin, the signals move at different speeds. This generates 0.6 picoseconds of delay per mil, pulling the data out of phase. Precision manufacturing corrects this by specifying spread glass fabrics that flatten the fibers into a homogeneous layer, or by utilizing off-angle routing to average out the dielectric exposure across both lines. Allocating budget micrometers with absolute accuracy. That dimensional stability is equally critical for internal via metallurgy. This diagram shows a high aspect ratio via hole. Standard direct current plating struggles here, depositing uneven copper layers that bulge at the corners while leaving the center walls dangerously thin. High reliability boards utilize modulated pulse plating instead. By intermittently reversing current cycles, the system drives copper ions deep into the structure, achieving over 80% throwing power and strict IPC Class 3 compliance. These advanced fabrication methodologies ensure the physical board matches the mathematical intent, preventing latent thermal cracking during high-stress operations. All of this microscopic precision ultimately bottlenecks. When we zoom out to the macro level to examine aerospace components, medical implants, and autonomous driving modules, the operational margin for error drops to zero. Aerospace boards endure extreme thermal shocks, ranging from -170 to +200 degrees Celsius. Under those conditions, the strict plating tolerances of IPC 6012 Class 3 are a legal necessity. Medical electronics and advanced driver assistance systems carry similar mandates, requiring conductive filament-resistant materials and perfect trace geometries to maintain zero-latency sensor performance. This diagram brings us back to the total cost of ownership. By deliberately factoring high-fidelity processes like laser direct imaging, pulse plating, and NEI-PEG finishes into the unit cost, you mathematically neutralize the massive downstream risk cost associated with field failures and warranty recalls. In the gigahertz era, calculating value based solely on the bare board quote is an economic illusion. Organizations that prioritize precision surface fidelity over unit price are the only ones equipped to survive the complex physical realities of high reliability